This morning, I welcome Gaël Varoquaux, which is one of the core developers of scikit-learn, and which will give both an introduction to scikit-learn and its ecosystem, and how it is developed in an open source way. Thank you very much.
Okay, so hi, welcome everybody. I'm Gaël Varoquaux, and the goal of this talk is a bit to share with you, like to give a bit of an introduction to scikit-learn and machine learning, because maybe not all of you know what machine learning is, and also to share basically why scikit-learn and how scikit-learn. And I'm going to start by why scikit-learn. And a few years ago, we decided to make scikit-learn really because we wanted to enable people to do things. I come from physics. I have a background in physics. And so I see these tools as a means, something to be used, and not an end. So we're in between machine learning research and applications. And our goal is really to make it easier for people to use machine learning. And so the goal is machine learning for everybody and for everything. By everything, I mean we're not interested only in computer vision. We're not interested only in marketing. We're trying to provide a common tool for all kind of applications. And one thing that we're trying hard to do is to avoid forcing you to learn too much. And the reason being that machine learning is, for many people, one out of many, many other tools that they're using. And so if every tool requires a month of learning, it's going to be hard to get something done. So that's the vision in 2 sentences. And let me introduce a bit machine learning. So machine learning can be defined as how to make prediction from data. So I'll try to keep an eye on time. Historically, it can be seen as growing out from artificial intelligence. So let's say in the 80s, in the early days of artificial intelligence, something that was done a lot was to build decision rules. So suppose that you have a bunch of objects here, and you're going to want to make decisions on these objects, so you're going to ask a finite set of questions. Is the object tall? Yes or no? Is it edible? Yes or no? Is it mobile? Later on, the idea came that you can learn those decision rules from observations. So just by giving data and saying to the machine, this is an orange, this is a car, and you keep showing oranges and car to the machine, eventually, hopefully, the machine will learn to distinguish oranges and car. In later evolutions of machine learning, I guess, involved more and more statistics. So more and more these days, we like to call these things statistical learning, which is the idea that you're going to model your data as a probability distribution function. You're going to accept the fact that there is some uncontrolled factor in your data, which you might call noise, and there might be many other sources of noises. And you're going to model this, and then you can start doing statistics and math and publishing. These days, you hear a lot about big data. So everybody is talking about it. Nobody really knows what it is. But for me, what big data is about doing the same thing, but with many more observations, which allows you to combine a lot of simple rules. And because you're combining a lot of them, you're explaining well your data, and you're able to predict really well. So there's this kind of evolution where you go from fixed rules that you control well to modern things where you don't control the rules at all, but hopefully you've seen a lot of data and you're able to do good prediction. Now, big data is the thing everybody talks about, and I have the impression that people talk less about machine learning. And this is a quote from Steve Jurvetson, who is a venture capitalism in the Silicon Valley, one of the guys that make a lot of money by making the right decisions. And he claims that big data without machine learning is not interesting. And the idea being that piling up data and not knowing how to do something out of it isn't interesting. So I think that we hear a lot about big data in the news, and below this, hiding below this, we need to worry about machine learning. One example, you came back from vacations and you have pictures of your friends, so photographs. And you know that you were on vacation with Andrew, Bill, Charles, and Dave, and you want to train a machine to recognize your friends. So this machine is called Facebook these days, but this is a machine learning problem. The problem is, it's more like this, you know, it's not a perfect picture of your friends. And then the machine learning problem is, from this set of labeled images, can I learn how to recognize who this guy is, okay? And it's not exactly the same image because there is a bit of noise, right? So there's a very simple method, which is to say, I'm going to store all the images, all the already labeled images of my friends in a database. And if a new image comes in, I'm simply going to find the one that looks the most similar to this new image. And I'm going to say, well, this image is the same person than the one that looks most similar. Okay? This is known as the nearest neighbor method. And just to see if you're sleeping or following, how many errors will I get? How many chances do I have to get it wrong if I show to my nearest neighbor, if I show an image that I have already seen, that is already in my database? Okay, 0 errors, right? It will never get it wrong because it's already in the database. Now, if I show an image that it hasn't seen, I will probably get errors, right? So this is telling me something really important for machine learning, which is that the error I'm getting on data that I've used to train my machine learning object is not the error I will get on new data. So in machine learning jargon, we say that the test error, the error on test data is not the same thing as the train error, the error on train data. This is extremely important. Now, there's another kind of problem, which is to say I'm going to try to predict a continuous variable. So in French, we say I'm going to try to predict the age of the captain of the ship, l'âge du capitaine. So this is what we call a regression problem. We're predicting a continuous a variable. And for instance, we could say, well, it may be a linear factor of the size of the ship. You know, bigger ship, older captain. That's a simple linear regression problem. We can see it as a machine learning problem. Now, we could also do a nonlinear model, right? Maybe the function between the captain and the size of the ship is not a linear function. Now, which one of the two models do you prefer? I mean, this one is really fitting the data much better, right? So we should prefer this one. Okay, so I think people prefer this one, right? So that's what we call the problem of overfitting, which means you're minimizing your train error, the error on the data that you've already seen too much. And you end up learning noise. So as we've seen, minimizing error on the train data is not always the best thing. Once again, the test data and the train data are not the same thing. So this leads us to the general notion of regularization. So here we have a family of method. They actually spline with a different smoothing kernel. So we have a family of different models, and we can ask which one do we prefer. And now answering this question is a difficult problem, but tuning this parameter that is the smoothing parameter of the spline is the idea of tuning a regularization parameter. We're going to try to prefer simpler models for a certain definition of simplicity, where the definition of simplicity depends on our understanding of the problem. Now, suppose, well, you know, the size of the ship isn't enough to completely characterize the age of the captain. So maybe we can look at the age of his daughter, for instance. So then suddenly we get two descriptors. So we have one output variable and two input variables. So that's a two-dimensional regression problem. So we've moved from 1D to 2D, and we have more parameters to learn, okay? We might have an offset, which we tend to call intercept, and two coefficients to control the slope. Now, this is a more difficult problem, right? More parameters to learn, more difficult problem. In particular, if I have only 2 data points, I cannot really learn the thing well, okay? It's going to be extremely noisy. So the idea here is that the more parameters, the more data point we need. And it may not be obvious on this side, but it tends to be exponentially more, okay? So this is known as the curse of dimensionality. And that's the problem machine learning faces, which is that as models are getting richer, as our data is getting richer, we're having more and more parameters to learn, which means that we need more and more samples, right? So that's typically a problem that machine learning addresses, and the way it addresses it is through regularization. Out of all these models, we're going to prefer one that is simpler for a certain definition of simple. So one very common example is I'm trying to learn to recognize handwritten digits. These are all handwritten digits. They're real handwritten digits. So for instance, here you have a 4, and here you have a 0. And they're actually fairly close. This 4 and this 0 are fairly close. The 1 and the 2 here are fairly close. So to go from these images to a machine learning problem, I will have to extract some descriptors, because I need numbers to put in my machine learning algorithm. So I will represent them with here 2 numerical features. So those descriptors I call features in machine learning. So why 2? Because I can show 2 features on a screen. And then my data becomes points on a 2D plane, right? So this is real data. These are actual points. You can see here that this 4, which looks like zeros, is pretty much in the middle of zeros here. So I've put colors in here, but learning a decision rule in this plane on how to classify digits, we call this classification. So on how to classify digits is pretty much learning separations between those islands, okay? So that's a picture of a classification problem. I'm trying to learn decision frontiers between islands of a given class in a space, which could be n-dimensional, that represents this data, all right? So that's like the abstract vision of what we call classification, which is recognizing different objects. All right. There are supposed to be labels here, but they're not showing up. So this is a plot of the stock market structure. And what's interesting here is that we didn't give any labels to the algorithm. We just took the data from the stock market and looked at the fluctuation of the stock market. And then we plotted close to each other companies that were fluctuating together. And so what's interesting here is that we don't know the structure. We don't know which company should go with which other company, but we're plotting them together. And what you cannot see here is that they group together with a fairly meaningful group. So I think here there's ExxonMobil and Shell and British Petroleum. So basically, I believe, I seem to remember that these are the petrol companies. Here you've got Yahoo, Google, Microsoft, Facebook. And this makes sense. You know, these are the same markets. You know, here you have the IT market. Here you have the petrol market. And because they're the same market, they tend to co-fluctuate, okay? So it makes sense that we can grab structure here. Why is this interesting? Well, because in general, it's much easier to get data without labels. It's costly to label data. You might have to pay somebody to look at images for a lot of time in labeling, to label the data. Or you might be Facebook and you might have to trick your users into putting the names of their friend on the pictures. So there are a set of problems which are known as unsupervised problem, They don't have labels, therefore they're unsupervised, which work with unlabeled data. So I've just given you a short overview of a different set of machine learning problems. So we've talked about regression problems and classification problems. These are two supervised problems. There's a bunch of unsupervised problem, which is basically finding some sort of structure in the data, which we may then combine with a supervised problem. And important notions are notions of overfit, which is basically explaining my trained data too well and eventually explaining noise, and test error, which is not the same thing as train error, okay? And usually when I'm looking to applications of machine learning, I'm trying to minimize the test error. So machine learning is really everywhere. It's in image recognition, for instance, on Facebook. We hear a lot about applications in marketing or financial sectors, but also if you're using any kind of online music system or online movie system, it's recommending to you new music to listen to. That's what's known as recommender systems. It's a machine learning problem. It's used more and more for medical data. So it's used absolutely everywhere. So scikit-learn tries to address all these use cases and therefore addresses none. Which means that when you want to apply it to a certain use case, you need to adapt your use case to scikit-learn. So why yet another machine learning package, right? If we're going to reinvent the wheel, the danger is to make it square. And a few years ago, so now I think it's been somewhat successful, so now we don't have to justify ourselves. But a few years ago we had to, and I think that that was legit because there were already machine learning packages. So the first thing is that real statisticians use R, right? You know, go in every statistics department and they will be using R. Fine, but real astronomers use IRAF. You probably don't know what IRAF is because you're probably not astronomers. But if you're an astronomer, you use IRAF. If you're an economist, you're probably maybe using GOES. If you're a real coder, you're using C, or maybe still using assembler. If you do physics, you're doing LabVIEW. I can tell you you're doing LabVIEW. Oh, if you're a statistician, but you're Bayesian, you may be using bugs, or maybe STAN. What I'm trying to tell you here is that this is a Babel tower. You know, if every micro community has its own language, we're not going to go anywhere. And our goal was to solve problems that were beyond statistics and machine learning. So for this, we choose Python. Because Python is a general purpose language and because we can use it to do all these things. And because it's already used in the wild to do applications. So that was something that was extremely important for us. So it's general purpose. It's interactive. Coding in C++ interactively has been done. It's not fun. It's easy to read and to write. And that was very important for us because we think that there's a lot involved with teaching these things. So, and nowadays in France, Python is used to teach a numerical computing, and we're very happy about it. And we're trying to make it easier to teach machine learning, and we're trying to have people that are basically ready to go and do things very quickly. Also, something that was extremely important for the choice was the scientific Python stack. So through the years, Python has developed a very strong scientific stack that was meant to solve problems like computational fluid dynamics or astrophysics or thermodynamic, so unrelated to data, but it means it has a very strong numerical core, including first the NumPy array. So what is a NumPy array? You can think of it first as, say, matrices and vectors and n-dimensional structures. But what they really are an abstraction over a float star in as many stars as you want. Okay? What I'm trying to say here is that NumPy arrays from the Python side look like high-level objects. but you can look at them from the C side or from any other side, and they're a very simple memory structure, which means that we can couple many kind of algorithms together with this memory structure. That was important for us. Now, the downside is that it has no annotation or no structure. So I remember in 2010, we got a review on an abstract for a conference for scikit-learn that told us, you can't do machine learning with NumPy arrays. They're not rich enough. You need more to do machine learning. And we wanted to use the less rich abstraction that could allow us to do machine learning because it was what would be common. It has a cost, which means that we can't annotate data, we can't put different data types together. So I'm thinking, for instance, of pandas, which is richer, but less universal. So NumPy arrays are universal across application. We will do image processing and machine learning with the same data structure, and we think it's important. And they're easily shared with other languages like C or Fortran. The good thing is once you have these, you can connect to the whole scientific Python world. To SciPy, so it's basically numerical algorithms in Python and C. To scikit-image, we'll have a talk about scikit-image later, so image processing. To pandas, so rich data structures. And I think the value of the ecosystem is really about plugging things together, because a machine learning toolkit by itself has no values for application. It will need something to go towards the application, whatever the application is. Also, one thing that was extremely important for us is that we wanted the code to be Pythonic, which is basically light with duck typing, so you don't have to worry too much about the types. And SciPythonic, by this I mean basically NumPy arrays and the ability to plug things together. That was extremely important for us. I think these are the reasons why we started scikit-learn. And our vision was we wanted to be machine learning for all, not only for machine learners. So no specific application domains, not too many requirements in machine learning. We wanted it to be high quality and Pythonic, which means that we worried about interfaces, and we wanted a community-driven development. So we chose a BSD license, so very open source. And also we tried to gather together a community of developers. So what we found is that there's a big tension between research. So I'm in academia. My function to society is to publish papers. And we find that there is a huge gap between a machine learning researcher and somebody who actually uses machine learning in practice. For a machine learning researcher, conceptual complexity is not an issue. If I make an algorithm 10 times more complex and I gain 0.1% in prediction, it's fine. I'll get a great paper out of this. Anything that's new is better. Just new is better. In science, we say novel. And simple problems are just old science. They're boring. We're not going to look at them. It shouldn't be simple. In the field, actually, tried and tested stuff, which means boring if you're doing research. It's really great. You know how it works. You know it won't break. In the field, you would like to ask not too much sophistication from the user. So you shouldn't expect the user of machine learning package to be fluent with a Riemannian geometry, unfortunately. And the API of the package is more important than the math, much more important. And when we started scikit-learn, some of our colleagues told us, you're focusing on the wrong thing. This is old. This won't give you success. So what we've learned is that solving simple problem matters. And solving them well matters a lot. So it matters more to solve simple problems well than complex problems not very well. So that's kind of the contrary of research. All right, let me move on to the tool itself because time is running. So what this is a Python library for machine learning, right? So it's a library. It's not a program because we believe that libraries are more expressive and flexible than a full program. So we keep getting this request. We keep getting people that come to us and say, I work in the insurance sector. And we have this type of data and this type of analysts. And the analysts cannot code. So if you were to do a graphical interface on top of this, then the analyst could look at the data, and then you'd be rich. This is not the problem we're trying to solve. We're not trying to be rich. So it's a library, and we want it to be extremely easy to use if you can code Python. There's a central concept, which is the estimator. The estimator is an object that can be instantiated without data, so you're not giving it any data when you're instantiating it, but you're specifying all the parameters. So you're describing the method. You're describing what you're going to do to your data. So for instance, if we want to look at the nearest neighbor, we're just importing a nearest neighbor, and we're instantiating it, saying I'm going to use my 2 nearest neighbors to predict. So that's our estimator. We have it. We can play with it. Now you need to train it on data. So you're going to call the fit method of the estimator on the data and the labels. X is the data and Y are the labels. And X will be a NumPy array 2D. So it's going to be number of samples. How many observations do you have? By number of features. How many descriptors do you have? So that's your input data. And the corresponding Y will be a 1D array, so 1 label per training data. And it will have either integers, if you're trying to do a classification, or floats. This is actually not true. You can get slightly richer data, but this is the basic idea. So if you're able to put your data in this shape, you can use scikit-learn. And then, new data comes in. You call the predict method, and this time you only have the data. You don't have the label, and the estimator guesses the label and tells you what the labels are. You can also call the score method, which could... Oh, I forgot the transform. Sorry, this one is really important. You can transform the data. So suppose you're going to want to change your data in some way. The estimator can learn on the trained data how to transform the data and then apply it to new data. We'll see how this is important. And you can also test give a certain score to data. So one example of transformation is when you're trying to learn from text. Raw text is not numerical features. It is not a 2D matrix of numbers, samples by feature. So you need to transform a bunch of documents into a data matrix. And a simple way of doing this is simply to count words. I'm going to count in each document, I'm going to count how many times a word occurs. And I will therefore transform my list of strings into a set of numerical vectors, which are the word occurrence. Okay? In scikit-learn, this can be done using what we call a vectorizer, which is a transformer, just like we've seen before. So you give it a list of strings, and it outputs a numerical matrix. So we have a very rich feature set, and I'm not going to cover it. But we cover supervised learning with different kind of models. We cover unsupervised learning with different applications. And we also have a model selection, which is basically comparing different models to choose which one works best, or tuning things like regularization parameters to choose the one that works best. This is a very old slide, so the numbers are not up to date, but it's just there to say that we're trying hard to be reasonably fast. And the trade-off is we don't want to go into crazy complexity to gain 2%. This is good for publication, but not for putting in application, because the code becomes very hard to debug. One example, and this is a slide that I've stolen from Gilles Loup, who's sitting somewhere in the audience, Gilles over there, and who will be talking about this later. But this is a comparison that Gilles did for random forest. So random forest are a very common algorithm with the common libraries that you can use to do random forest. And this is in fit time. So if you're looking at fit time, we are faster than basically all the common open source libraries that you can have. This was a lot of work. Not by me, I don't do random forests, by Gilles and others. Okay, what do you do if your data doesn't fit in memory? I promise I talk a bit about big data. And these days, you know, when you have big data, you use Hadoop, you use things like Spark if you're cool, and you use distributed storage and a computing cluster, and you hire, you know, 2 cluster administrators, 2 Spark administrators, and your team becomes really big, and basically you've become a big data factory. Most people want to process their data on a MacBook Air. This is my experience with people. Seriously. They don't have petabytes, but they still have too much data for the RAM of their MacBook Air, and they want to do Python. So there's a simple solution for this, which is that you're going to grab chunks of your data and you're going to feed it to the algorithm, chunk by chunk. So you don't have to load all your data. You're taking a chunk, you're feeding it to the algorithm. And some of the algorithms in scikit-learn can do this. They expose what we call a partial fit, and basically you're giving it a chunk of data and label. The algorithms that can do this are, I don't think this list is exhaustive, are linear models with stochastic gradient descent, SGD, for regression and classification. We have 2 clustering algorithms that can do this, and new in the release that just happened, we have an incremental PCA. So if you're PCA, principal component analysis, is basically a data reduction algorithm, and we now have one that will work out of core. So this can be really useful to reduce huge data sets. Another trick that you can use for data that does not fit in memory is on-the-fly data reduction. So the idea is that you have many, many, many features, and when you have many, many features, chances are that there is not independent information on all these features. They may be correlated, they may be noise features. So you're going to reduce the data as loaded. So once again, it's going to be the transform pattern. I'm going to call estimated or transform, and I'm going to get a small x from a big X. So then, for instance, I could change this with an online algorithm, and I could go from absolutely huge data that is huge in both directions to something that I can fit with scikit-learn. And the kind of algorithms that we have to do this are things like random projections that will randomly average features. Works really well in practice on things like images. We have feature agglomeration that will put together features that look similar. And for text data, there's the hashing trick that basically will map complex text to a hash table. All right, very quickly, I'm going to talk a bit about the project. And importantly, this is a project with many, many people. And I think this is key to the success. So this is the not up-to-date graph of the number of lines of code in scikit-learn. So you can see that it keeps growing and growing. This is not up to date. It didn't stop growing in mid-2013. And why is this happening? Because we have a huge team. And why do we have a huge team? Because we're open source and because we try hard to work together. And we have quite clearly more than 200 contributors. The real number is hard to say because some people have just fixed a typo in the documentation. That is a contribution, and some people have spent many years on it. What I think is important is from the start we've had a full staff programmer working in scikit-learn. These days it's Olivier Grisel, who's up there. And such a person is extremely important because even though he will account for only a small fraction of the lines of code, he's the person who's basically holding the project together. And also doing the ugly things that people don't want to do but that are really important for the project. He's the person, he's the captain, the person who keeps the boat on track. So this is an old number too, but the estimated cost of development is in millions. And that's because we've been able to aggregate work from many, many people. And one example of what this does, and this is a tweet from Gilles Loup a year ago. And this shows, these bars, like this, shows the speed across the different releases of random forests. So you can see that random forests have gotten, so these are different kind of random forests, and they've gotten much, much faster. This has happened because people have just worked on them again and again and again. And it's not only Gilles, it's a large team of people that have worked together, that have looked at each other's code, that have suggested improvements to code. And those improvements, because they come from different people, they're going in different directions. So at the end, you're adding up improvements, and you're getting an impressive speed up. The reason I'm saying this is that's the benefit of putting code out in open source, and also doing the work to have a community around it. Your code improves almost by itself. So this doesn't happen by itself. You need to focus on building a community. And so these are the things I think are important. One of them is to focus on quality. You know, developers like to work on good code. They don't like to work on bad code. It's as simple as that. So if you put crap code out, you will not have contributors. It's important to build great docs and examples because people feel that when they're contributing to your project, they're getting more visibility than when they're leaving their code alone somewhere. I claim it's important to use GitHub because it's the place where all the geeks are, and that's where you want to be. This one is important. It's important to limit the technicality of your code base. If you put too many very complex things in your code base, the number of people that can contribute to this code base will dwell down to something tiny. So for instance, if I want you to understand medical imaging, 3D visualization, and machine learning, because this is the problem I'm trying to solve, I'll get a handful of people working on my code base. Releasing is extremely important, and what's important is at some point you have to let go. Even if you wrote the first line of code for the package, you have to let go decision power. Elsewhere, your contributors will not be motivated. That's really important. How we work via pull requests. So we do code reviews on GitHub. So basically, somebody submits some work, and we look at it. We as a team, everybody, looks at it and does comment on it. So this is good because anybody can do this. We can include newcomers, even though the bar is a bit high. This is good because we read each other's code. There's a rule that says that we cannot put code in scikit-learn if it hasn't been reviewed by 2 core contributors, which means that no code has been seen by only 1 person in scikit-learn. And that really improves both the code, but also the social dynamics. We find that nowadays everything is discussed in a pull request, and it's a lengthy process. The first thing that we tend to discuss is, do we want the algorithm in or not? Because if we put every publication in scikit-learn, it would be huge and completely unusable. So we need to make a choice whether it should go in or not. We worry about things like defaults. You know, what will the user use this algorithm for? So what default should we put in for parameters? We worry about naming, about numerical stability, about performance. All this gets discussed over and over and over, and through this process, the code improves. Another very important aspect of quality in scikit-learn is unit testing. We try to have everything unit tested. So, Olivier, do you remember what our current code coverage is? 94, 95. So that's pretty high percent. That's pretty high. So it's a goal, and we found that it was great for numerics. So if we have a minimization algorithm that should, minimize with the cost always going down, we test this. And we find that, when the data is very ill-conditioned, well, sometimes it doesn't minimize. So then we go back and see where the numerical instability is, we fix it, and we test again. And by doing this process over and over and over, we're getting more robust algorithms. Why is this important? Because if you go out in the field, you don't control the data you have, and somebody is going to put crap data in your code. And somebody may be you, actually. This is also one thing that we also do is that we have a set of what we call common tests that we try to run on every single estimator. Basically, on every single estimator, we try to instantiate it, fit random data, predict, put nans in, see that when you put nans in, it doesn't crash or segfault, but gives maybe a good error message. We check things like this, and this helps us making sure that our code base is consistent. All estimators behave in a similar way. And we found also that that really helps improving the quality. So we test for things like side effects. Okay, so basically what we're trying to do here, what we've done, I think, is the standard mantra of development, which is make it work, make it right, and then make it boring. Because if a problem is boring, it's solved. You know, if you're not thinking, last year at PyData London, I think I heard somebody say, machine learning is the easy part. We just use scikit-learn. The hard part is going from our raw data to something on which we can do machine learning. If this is true, which is probably not always true, but if this is true, we've won, it's boring, that was our goal. Now, the problem with this is that once it's boring, people don't want to work on it. So in scikit-learn, we have a lot of boring things to do, like looking at other people's code, which we force ourselves to do, but of course we prefer coding. So the reason I'm putting this slide up is that we need support. The support is mostly acknowledgement. And it's not only about papers, it's about if you're in companies, just saying that you use it. Because so this year has been a good year. We've gotten a lot of funding thanks to people who are in the audience. But for a long time, we didn't get any funding for scikit-learn. And it was massively used, and we were not getting funding. So we were worried. Now, this year has been a good year. So it's doing great. Another thing that we've learned is that it's incredibly hard to scale. So scikit-learn has gone from a small project to a big project. And things have just gone much harder everywhere. Doing something 5 years ago was much easier than doing something today. And we have crazy user support. I think we have an exponential increase in number of support requests. And we have a growing code base that is becoming harder and harder to understand. So I'm just saying this just to say that there is a difference of scale between scikit-learn and a small package that does only one thing. So to wrap up, our vision is basically to be an enabler and to be machine learning to solve problems. We want to be a versatile library, which means that we should not be application specific. So we need the exact right level of abstraction. We need to make it easy for you to use an algorithm, even if you don't understand it. But we don't want to dumb it down and hide the internals. We're trying to float in between the research and the application. So I've talked about the tool. We hope to have a simple uniform API across Learner. That's something we've put a lot of investment in it. And it's all NumPy based, which is a pro and a con. And finally, about the project. I think the project, what is really interesting about the project is it's about many people that are working together. And what we find is that getting all these people working together is improving our quality. It's helping us not being domain specific. When you have people doing natural language processing, so a marketing like data science and vision together, so image processing, they all have different data types. And having an algorithm that works on all these data types is a benefit to all of us. I've learned a lot of things from the people doing natural language processing. And finally, we're hiring. So in my team and also in Alex Grandfort's team, and we're hiring to work on these things. We're hiring to work on open source libraries, and that's important. I just said before that we needed support. We've gotten support, we've gotten funding. Now we need people to work with us. We need good people that are motivated by these problems. Thank you.